right, welcome back to CS50. This is the end of week 3. A couple of announcements. If you still need to make any changes to your section, please do so today. You can email help@cs50.net. Otherwise, follow the directions that were in the email that the bot sent you this weekend regarding your section assignments. A few invitations as well. So Zynga, makers of Farmville, which may appear a little too often in your Facebook walls, is here today, 6:30 p.m. In a recruiting capacity in Maxwell Dworkin 119. Maxwell Dworkin, for those unfamiliar, is the CS building down the street on the left on Oxford Street. It looks like there will be free food and free giveaways and bring resumes and win an HP mini notebook. So that's 6:30 today. For those of you looking for interns or full-time roles, Brian Kernighan is the man who taught me CS50 years ago. He's faculty at Princeton and is here on sabbatical this fall. And he's actually going to be giving a talk tomorrow and giving out ice cream. Tomorrow at 3:30 p.m. will be ice cream in Maxwell Dworkin, which is actually a weekly tradition over at the School of Engineering, followed by his talk at 4 p.m. I remember this man, frankly, because his first lecture has far outshined mine. He stood up on stage, had apparently spent the summer growing a nice beard, and then his algorithm was not putting on socks, but was how to shave using hedge clippers. It's something that stays with you for some time. But the talk he's giving on Thursday, for those of interest, and realize too, as if my being in 50 now is any indication, he's very much adroit when it comes to speaking to non-technical or less technical audiences. Do not fear, it will be over your head. The changing face of programming is his talk tomorrow. The rapid evolution of languages, tools, environments, and expectations presents major challenges and opportunities for programmers and for software engineering education. This is true across all kinds of programming, but is especially true for web systems, which are now routinely written in untyped scripting languages and include AJAX, mashups, toolkits, frameworks like Rails and Django, and a profusion of interfaces, all operating asynchronously on distributed systems. A few new pieces of jargon there that we will touch upon towards semester's end. The growing popularity of phone applications has not made life easier for programmers or instructors. For the past 10 years, I've been teaching a course on advanced programming techniques that is more and more stretched between important old material and new unproven material that might be important. In this talk, I will illustrate some of the challenges and discuss ways in which we might use complexity and rapid change to advantage. He's a wonderful man and a wonderful speaker, to be honest. So if you have some time tomorrow for a little ice cream and talk, please do feel welcome to join. And finally, Facebook. Facebook is a social networking website. They will be here on Monday in the form of Thomas Carriero, who's one of CS50's former head TFs, also in a recruiting capacity. Lunch will be served. For those unfamiliar, or for those a little intrigued by the opportunities that await in Mountain View, Facebook is hiring brilliant engineers who want to make an impact as we grow and shape the way the world connects and shares with each other. No one has ever done what we are trying to do at such speed and scale. On top of that, we do it with only about 500 engineers. Our active user to engineer ratio is over 1 million users to 1 engineer. And growing. You won't be able to get that personal impact in any other tech company in the world. So if you'd like some lunch, if you'd like to reunite with an alumnus and like to hear a bit more about Facebook before class, Monday, 12 p.m., Maxwell Dworkin, not G119, 119, which is one floor upstairs. All right. So we left off last time with a whole bunch of pieces of paper on the wall. And the challenges of the day were, here's an array. And unfortunately, it was unsorted. These were just semi-random numbers in some random order. And the challenge at hand was find the number 50. Now, a reasonable person, as a reasonable person, we might start at the left and then move our array rightward. And you might start to realize, all right, this is a bit of a game and jump ahead at some point. But for the most part, you can't do much better than good luck when it comes to searching an array of unsorted integers. You might have some heuristics, but again, at the end of the day, if you don't know anything about those numbers, it really is just guesswork. Now, in fairness, it was deliberate on my part that I put 50 all the way over here just for demonstration's sake. But in the real world, that very much could happen. And one of the themes today and moving forward is going to be this notion of worst cases, worst possible inputs. And in the worst possible case, in that small problem, the thing I'm looking for is all the way at the end, which means I have to do a huge amount of work just to find a single value. Now, thankfully, there's approaches that are more intelligent than that. And we did this in the first day with the phone book, and we did it last time with the second array of numbers. And the key difference there was that the second array of numbers was sorted. And this simple little detail was a huge advantage, right? In the real world, you can imagine the nightmare it would be if Verizon just published a big book with numbers in the order in which people signed up for telephone numbers, right, from left to right. Well, you'd have to search the whole damn phone book, or at least half of it on average, to find some random friend whose number you're looking up. Well, same here. If you don't know anything about the numbers, you ultimately might have to check them all, but not the case if those numbers are actually sorted. And so one of the questions we'll look at today is, if you are given a seemingly random sequence of numbers, not even necessarily that large, what are your options for actually sorting this? Now, we'll use numbers because they're easy to talk about, but in the context of Facebook, for instance, you might want to sort your friends. You might want to find friends of friends. In the context of Google, you might want to search or sort web pages. So certainly could you apply what we'll look at in this small context of numbers to really any types of objects that you can impose some sorting on. But first, some new tools for your toolkit. Thus far, printf has probably been your primary tool for debugging. To debug a program means to find the bugs and remove them, or to chase down logical errors that you might have made, or even syntax errors that you might have made. Now, if you've made a syntax error, that is, the characters you've typed at the keyboard just don't belong where you put them, you put a semicolon in the wrong place, you forgot a parenthesis, well, GCC, nicely enough, will just yell at you before it even finishes compiling, telling you, I can't compile this because I don't know what you mean. You've expressed yourself in an incorrect way. But very often will you actually get your code to compile, and you'll be able to run it, and then you'll get segmentation fault, which we've seen already refers somehow to memory, and more on that next week as well. You might just get the wrong output. You might get the wrong answer. You might get no answer whatsoever. And at this point, your code, yes, compiles, but it's surely not correct. And so you might go back in, as you have been, inserting printf statements here or there, printing the value of this variable, printing out what the user just wrote, just to do some sanity checks for yourself. And presumably you delete those printf statements before you actually submit and call this program complete. But this is a little bit hackish, right? And as programs get longer than a few dozen lines, a couple hundred lines, inserting printf statements all over the place and then recompiling your code, rerunning it, going back and changing the printf statements, this really isn't the happiest workflow. It doesn't scale very well, and it's just not very interactive. You have to kind of do make the change, compile, run, make the change, compile. This is 3 steps just to accomplish a relatively simple goal, which is find my problem. So thankfully, there exist tools. And one we'll look at today is called GDB, the GNU debugger. This is a program that you run at the command line, just like GCC itself. But what happens is, once you compile your program with GCC, you, of course, get your executable, your binary, the program, like a.out or Caesar, or whatever the program is called. What you do with GDB is you run GDB, but pass it, your program, as an argument. And what GDB does for you is essentially runs your program for you line by line by line, but slowly, so that you can watch things happen step by step. And you can set what we'll call breakpoints, which is to say, if you only want to see what's going on at line 20, because you're pretty sure that's where you're having some issues, you don't have to step through the first 19 steps. You can just say break at line 20, enter, then run the program. It will run terribly fast, and then pause at line 20 for you to then poke around at what's going on inside the computer. So it's going to feel a little arcane at first in terms of interface. You'll find a nice cheat sheet on CS50's website on the resources page. But what I thought I'd do today, and you'll see in section in the weeks to come, are some new tricks of the trade. And to be honest, with just a few commands that I'll use myself here, you can get a lot done. So I'm going to go back in time to a program we used last week, which was called Buggy3. As the name implied, it was in fact buggy, not because it didn't compile or because there were syntax errors, but what was the problem with this swapping program, if you recall? It didn't actually swap, right? I claimed this swap 2 numbers, and yet we dug in a little deeper, right? I used a printf ad nauseum here, and it did actually swap those numbers when I added a printf at the very bottom of my program here. But then as soon as swap the function returned, just looking for my laser pointer, as soon as swap returned, it seemed all the hard work we had done was for nothing, and the values remained unchanged in main. All right, so this is an approach that you might reasonably take with printf, printing out everything you want to see line by line. And then, as I did too, once I was done, I deleted that line from swap because I don't want to print it out all over the place. I just wanted to print it out for debugging techniques. Well, let's do this instead. Let me go ahead and quit Nano. I'm going to go ahead and make Buggy3. And notice this. There's a whole bunch of stuff that's been flashing on the screen the past couple of weeks. And some of them we've talked a little bit about. For instance, -L CS50. It's wrapping from over there. That, of course, means Lincoln CS50's library. -LM, little sanity check, is the math library. So you can use functions like round and a few others if you need them. For those doing the hacker edition, -L crypt means so use the crypt function. So for those tackling the hacker edition, it involves cracking or decrypting passwords. And there exists a function called crypt for that. And it is, among other functions, in a library called crypt. Now, what's this other stuff? Well, some of these things are flags, as we call them, that have been configured by us. We've pre-configured make on the cloud for you. And though you might resent us for this, -W all, or rather -W error, means even if there's the slightest syntactical mistake in this program or thing you really shouldn't do, yell at the student and refuse to compile the code. So this is deliberate in that it really forces you to get things perfectly right. But there are some side effects. Some of you might have gotten annoyed at the computer or at us because you could declare a variable x and you're not quite ready to use it yet. You know you want to use x, but you want to write some more code first, and it won't let you even compile because you're not using x. Well, again, this is a pedagogical tool, and it's also, frankly, a matter of good practice because there's too much code out there, too much code that's vulnerable out there that just hasn't been as rigorously checked as these little configuration options allow for. Now, for today, we're making use of this guy over here. -G GDB is a flag that we've been secretly including in make all this time. But what it does, as I think I said a couple weeks ago, is it adds to your program, your a.out, your Caesar, some additional bits that help a program like GDB follow along where you are. It includes things like line numbers, essentially, so that when you're walking through what is otherwise just a file with zeros and ones, there's still some reminders inside your file as to where those zeros and ones came from, what original line. So if you are still in the habit of running GCC manually at the prompt, that's fine. But henceforth, if you want to use GDB, you're going to have to include this flag as well manually. So we're already at the point, frankly, where you might as well just be using make because it automates all of this for you and saves you a whole lot of typing. So now I'm going to go ahead and run the program itself, which is called buggy3. And of course, it seems to, in fact, be buggy. And here are my printf statements that seem to be confirming that it is not, in fact, working. And just to be clear, let me go back in nano buggy3. And recall that what we did last time was I did a little sanity check. I said printf a equals %d, new line, let's say, comma a. So I want to print out the value of a. And then I want to print out the value of b. So this was my sanity check. So I'm going to save, enter. I'm going to recompile with make. And I'm going to rerun buggy3. And sure enough, it seems to be working. It starts off at 1, 2, becomes 2, 1, but then reverses back to 1, 2. And this is how we concluded definitively this thing is not working as intended. So let me remove these superfluous printf statements, because again, this isn't the best habit long term to get into. Let me recompile so I have the freshest copy. But now instead of running buggy3, I'm going to run gdb space buggy3 and then enter. You get a whole lot of stuff that's pretty useless, just warranty information and all this. But then you get a gdb prompt. All right, so at the gdb prompt, I get to do a few things, among them run my program. So one of the new tricks today, and again, all of this is documented in a cheat sheet on cs50.net/resources. I'm going to hit enter. It apparently runs your program. So not all that useful yet. I could have done this, a second ago at the original command line. But notice this as a teaser. When a GDB tells you program exited normally, it turns out that means that main returned what? 0, right? So as promised, returning 1 or 2 or 3 or 0 for success cases in main does have utility when you're using tools like this so that you can actually see what's being returned or be informed that it, in fact, all was well. So this was not all that useful, though. Just running my program, I want to know what's wrong. So I'm going to go ahead and do this. I'm going to type break. And then I'm going to type main. What's nice, and let me move this up to the top. I'm going to type break main. And this sets what's called a breakpoint, a pause point in the program at the function called main. Notice I get a slightly cryptic output, which is breakpoint number 1 is now at 0x. And what does this mean, perhaps? Yeah, so this is the address in memory. So we'll talk more about this over time. Frankly, it's useful for silly things like Photoshop colors and web colors. But hexadecimal notation is just another base system, like binary, which we've discussed, decimal, which we've grown up with. 0x typically denotes hexadecimal, which is base 16. And as we'll see, this is just a more compact way of representing numbers so that they don't get ridiculously long. So this just means in RAM, in my program's memory space, in RAM lives a function called main. the so-called text segment from last time, but more on that to come. And that is where it happens to live. Is this relevant? Not so much for us just yet. But as things get more advanced and we get more savvy, certainly details like that can help. But for us, it looks like we've set a breakpoint in this file at line 21, because that's apparently where main began. So now if I run and hit enter, notice that execution does break at line 21. So again, the output's a little cryptic at first, but this is just telling me what happened. This is saying, here's line 21. Here's what's on line 21. But it hasn't executed line 21 yet. In fact, it won't until I actually hit the command next. So I'm going to go ahead and hit next. And now I'm on line 22. X has already been assigned the value of 1, which I confirm by typing the command print. So it's not printf or anything like that. There's no parentheses. These are just commands in a program, not functions. Print x, enter. And in fact, x equals 1. Now, this thing here, the $ notation, is just handy if you want to get fancier and refer back to this same answer later on, kind of like in a fancy graphing calculator allows you to do. But for now, what we care about is that the answer is 1. Meanwhile, if I type print y, well, that's weird. How did y become 3,223,540? Because we haven't initialized it yet, right? So this is already a visual lesson that if you don't initialize variables in a program to something, who knows what they're going to be? This computer, the cloud's been on for several days' time. Even this program did some other stuff when we first started it up, unbeknownst to us, or that we didn't see visually. And surely the program might have used some of the memory that's allocated to my program for other purposes, if temporarily. But now y happens to live at a certain location, and it just has this garbage value, a meaningless value that I should absolutely not trust is anything legitimate if I haven't assigned it a value explicitly, as I'm about to in line 22. So even though I've typed a few commands, I have not proceeded to continue executing this program. We're still at line 22. So now if I type next, or if I'm getting a little lazy with keystrokes, you can just type n, the first letter or two of each command, n. Now I'm at line 24. So now if I do print y, I should hopefully see, in fact, the answer is 2. And again, ignore the $ stuff for now. It's what's on the right-hand side that's interesting. All right, so if I now type, next again, this printf line is going to execute. So I'm going to see the program's output commingled with GDB's. All right, so there it is. X is 1 on the left. Then I'm at line 25. Let me go ahead and I'm going to scroll things up to the top so you can see in front. Let's type next again. Y is 2. I claim in a moment that we're swapping ... So let's do next. All right, so here's an interesting decision point. This is a function call. I am about to, on line 27, call the function swap, which I wrote. Remember, it's lower in the file called buggy3.c. I'm about to call this function, and so I can. I'm going to go ahead and do next. That function will execute. Something will hopefully happen to x and y. Let's check. Print x. Uh-oh. Print y. Still nothing. So that function seems, in fact, to have had no effect. Now, this was not all that useful an exercise, because now my program's pretty much done, right? I claim swapped. I then claim that it's x is something, y is something. I now hit this curly brace. I hit next again. Now I'm in this weird part of my world, because remember, I've used other functions. I've used printf and the like. So don't get distracted if you see stuff that's clearly not yours. I know I'm at the end of my program, because I already saw this curly brace pass me by. So I'm just going to go ahead and type continue, which undoes the effect of break. It just says keep going. Forget about this breakpoint. I'm done caring. And now I'm, in fact, done with the program. It finished up whatever legwork it needed to do at the end. All right, so this was not all that helpful. All I did was very slowly discover what I'd already discovered before with printf. But here's the power of something like GDB. Let's redo this. Let me rerun, run. It's going to automatically start me at the beginning. I still have that breakpoint, so I'm going to hit it again. And now let me step through a little more quickly. Next with n. Next, next, next. Next. OK, here's an interesting point. Now I want to step into this function, because what's powerful about a debugger is you can poke around anywhere you want in your program. So I'm going to type step instead of next. Step means step into this function, whereas next means step over this function while still executing it. Enter. And now notice what I get as output. I'm being informed, OK, I am in the scope, as we've discussed, of swap. It was passed these two arguments. A is 1, B is 2. And the line I'm currently paused at is line 41 of my program. So here, too, it's helpful. If you have two terminal or two PuTTY windows open, have your source code in one, have GDB in the left-hand one, and you can watch things progress in the big window. So let's see. This is swap. Actually, I can also type list if you want to see in the context of GDB what code you're currently dealing with the line numbers on the left-hand side. But I'm on line 41, as this thing here says. So this is uninteresting at the moment, so let's do a quick check. Print the value of temp. And let me move it to the top. I'm going to print the value of temp. All right, 0. So it may be the case that just by happenstance, a variable seems to be initialized to some value, very often 0, but that's clearly not a guarantee. So do not trust that. So now let's go ahead and type next to execute that line of code. So now if I print temp, it should be, if you recall, I passed in 1 and 2. And I assigned it the value of a. So in fact, yep, it's 1 here. So temp is currently 1. Now I'm going to clobber the value of b. So let's do a quick sanity check. Print a, print b. And that's consistent with what I passed into swap. But here we go. We're about to execute line 42. And I'm going to do this just by typing next. Next. All right, so now I'm going to do it again. Print a, print b, and there it is. So we are halfway through the swapping process because now a and b happen to be the value of 2. Now what can we do here? Well, I can go ahead and just say, OK, next. Next, I'm kind of losing interest in this. And so as soon as that function returns, notice it reminds me, I'm back in main. I'm at line 28, and you're about to do this. So in short, you have this power with just a few commands. Run, break, next, step, and continue. You can do a lot of useful things. And there's yet more that we'll look at in section and is documented online. But let me show you one last trick that's not terribly useful for this program because it's so short. But when we start writing programs that have multiple functions that you wrote that get called in succession, watch what you can do. I'm going to hit run. And because it's not finished, it's going to yell at me. Start it from the beginning. That's fine. I'm done with this version, with this iteration. So Y for yes. I'm at the top of my program. I've broken as usual. I'm going to go ahead and type next, next. And you can do up, use the up arrows as before. Next. I don't want to type next here. I want to hit step to dive in. And now suppose this is a reasonably sized program. I'm actually getting disoriented with where I am, what I've stepped into, and whatnot. That's fine. You can do a little sanity check. You can type the command backtrace. And as the name implies, it kind of looks back in time at where you came from. And what it says is this. The place I am now is the first line. I'm in frame 0. So I'm in swap. I passed in these variables, and that happens to happen at this line. Where did I come from? In other words, how did I get to that line of code? Well, previously, in the other frame that is currently in my RAM, I started in main. So the reason this print's kind of in reverse order is actually consistent with that picture we drew on the board the other day. When we talked about RAM having stacks and frames that grow like this, it's the same idea. Notice that main is on the bottom and swap is on top. So if swap itself calls a third function, it is going to be located in RAM up here. And so pictorially, it's pretty consistent. OK, so a bit of a whirlwind tour. The next couple problem sets will encourage you and walk you through the process of using this to the extent you need it. But any questions on the usage, the concept, anything? Yeah? Absolutely. You don't have to set breakpoints only at main. If you have a function called swap, I could have typed break swap. Or if I, again, know that there's a certain line I care about, I could even do this. Break line, let's say 23, because I care about line 23. Then when I type run, it will start running from the top of the program as usual, but stop at that specific line. So it's actually quite versatile. Yeah?
Can you break, continue, then break again?
Can you break and then continue again? Yes. So the continue command is useful also in the context of loops. Because if you set a breakpoint somewhere in the middle of a loop, you might get bored with typing next, 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 next throughout all of these lines. You really just want to get to the next iteration or the next iteration. So if you type continue, it's not going to run to the bottom of the program. It's going to run as the logic of your code suggests. So it will iterate in this loop. And if you hit that same breakpoint again, you will, in fact, pause. Now, if you're iterating 100 times and you only care about the 99th iteration, this could very quickly get tedious. But you'll see in the online PDF, you can say, like, continue 98 times and then break. So again, you pick up little tricks along the way. Any other questions? Yeah?
So when you're doing this, when you're setting the breaks and stuff, like, can you have it instead of I know you can start it at a certain line.
Uh-huh. So you can't start execution at a certain line. Your program has to start at the beginning, but you can break at any line. And break just means pause here so I can poke around, and then it's up to you to decide if you want to continue execution by hitting next or continue itself.
So there's no way to start it at a certain
No. So if you wrote the code here, you're going to have to execute it from here to here. You can't just say start running my program at a different point. All right. So that's a little tool for your toolkit, so to speak. It might very well be useful for this P set if you're not yet done or not yet started. But for the next ones and ones moving forward, it's one of these things, honestly, where statistically many of you probably won't take this advice for at least a couple of P sets. But this is one of those things that certainly in programming, where if you spend that frustrating first 30 minutes, maybe an hour learning something like this, it will absolutely save you 10 times that much time by semester's end. When you get comfortable with this stuff, printf is not going to be your best friend for very long because it's so terribly limited and so terribly tedious. So invest this time, this week or next, just learning some of the basics of GDB. And honestly, it's one of those things that will absolutely help you help yourselves and in the end save you time for sure. So here are some numbers. And the goal at hand is to get to the point of actually having these numbers sorted so that we can actually find pieces of data more efficiently. Now, again, I've chosen some fairly simple numbers here up on the board. You could imagine gaps in them like we had on the chalkboard on Monday so that they're not just evenly spaced by one number apart. And you can certainly imagine each of these things representing a web page or a name in a phone book or anything that lends itself to actually being sorted. But how do we go about sorting something like this? Well, a human probably will just kind of scan the list and say, all right, there's the number 1. Let's move that. There's 2. And we all have some kind of intuition behind how you sort these numbers, just as a normal person probably already knows before taking CS50 how to find someone in a phone book pretty intelligently. Right? Before this class, odds are you were not starting at the beginning and moving from left to right. But how do we begin to now express what we as humans consider to be intuition, if not obvious, in a way that the computer can now understand so that it can do our bidding using our own life lessons, but far more quickly than we could ourselves. So if you don't mind, perhaps some fresh faces this time. I have 8 pieces of paper and need another bite of volunteers. If you'd humor me. Come on up. 2, 3. No one ever wants to come up from up here. There we go. 4, 5, 6, and 7. Let me see if I counted properly. 1, 2, 3, 4, 5, 6, 7. OK, good. And 8 in the red. All right. So if you could, first part is easy. Oh, and you have to be comfortable on camera before you step on stage. First part is easy. Line yourselves up, let's say over here, just so we have you all together in the same order as the projector is indicating now. All right. Thank you. All right. So line up, if you could, in this way. And so that you are not anonymous, we want to say who you are and one interesting thing, which might mean concentration, house, sport, extracurricular, whatever. And just pass it down.
My name's Chi. I want to do CS.
Very nice.
My name is Martin. I'm in the best house on campus, Elliott House.
My name is Louis, and I like yogurt.
My name is Daniel. I also have the grand fortune of being in Elliott House.
Hi, my name is Aziza, and I'm in LA too. Woo!
Hi, I'm Carl, and I'm from Leverett. I'm Ryan, freshman from Canada.
I'm Ian. I'm on the Alpine ski team. It's pretty fun.
All right. Excellent. All right. So now you know these 8 folks, and we have a couple of approaches that we might take here. So I'm going to propose one and then see if these 8 can help me execute this method. So as a human, I might take this step back and say, all right, number 1, I'm going to pull you over here. Number 2, but don't do that just yet, right? Because it's kind of, there's this intuition that presumably all of us have, and we could sort this list in a couple of seconds. Now, ironically, what we're about to do is probably going to take more than a few seconds. But once this input gets larger than n equals 8, and is n equals 1,000,000 or 1,000,000,000 or the like, surely some of these tricks will begin to leverage to our advantage. So I'm actually going to point out first, if these folks are implemented in a computer, they're probably implemented not as 8 variables, x1, x2, x3, because we've already introduced arrays. Odds are they are just called numbers, and the size of this array numbers is probably 8. And each of them is an int inside of this array. But the catch is with the computer, I don't have this sort of godlike ability to just look out on them all and take in all of these numbers at once. I have to be much more deliberate. In an array, you can iterate from left to right, from right to left. You can jump randomly via random access to any value inside the array by the square bracket notation. But you certainly can't see them all at once. So just for visual sake, if you guys could just turn your papers around so they're blank white on this side, I mean, this really is what the computer is handed. There's 8 numbers, yes, but I certainly can't take some aggregate view all at once. I have to look more carefully. So go ahead and flip back the normal way. And I'm going to propose a very simple heuristic. I'm going to start at the beginning, because it's just easy to iterate from left to right. I'm going to look at the first 2 elements, 0 and 1, index values, 0 and 1. And I see that the number 4 is at location 0, and the number 2 is at location 1. This is wrong, right? The goal at hand is to sort these numbers. So you know what I'm going to do? The simplest heuristic I can come up with, I'm going to say swap. Now go ahead and swap. Now, this took how many steps? Well, if we implemented this in code, it's like at least 3 lines of code. We need a temporary variable. Then we need to clobber A, then replace B, and so forth. Now, in fairness, our swap function's a little dysfunctional right now. We have yet to see a working version of swap, but that's coming. In fact, we'll introduce that and something called pointers next week that allows us to pass by reference and not by value or by copy. So let's take for granted today that surely there's some solution to this problem of swap. We just haven't done it ourselves yet. So I swap these 2 guys. And now what do? Well, I don't have to look at them just yet in a pair anymore. I can advance 1 step. So I++. Now 4 compared to 6 checks out. I don't have to do a swap, so I can take another step, I++. 6 against 8, OK, ++. 8 against 1, I need to do another swap. So that'll take few CPU cycles. Now, you know, I could start backtracking because clearly 1 should be going this way, but I'm going to keep implementing the same approach, right? You wouldn't change your code in the middle of a for loop. It's going to execute again and again in exactly the same way. So let's do the ++. 8 and 3. All right, ++. 8 and 7. ++. And 8 and 5. And now probably I do ++. My for loops condition or my while condition, whatever it is, realizes that I've gotten too big. And so I reset to the start of this list. So it seems like I have a loop that's going this way, right? So that's I++, I++. So I've looped through the whole array. So that would seem to suggest I'm done. I've looked at every value. But obviously, no. So just intuitively, how many more times am I going to have to come back to the end of this list, much like a typewriter going back to the carriage return, and go again? If I do it once more, will it fix the problem? No, so maybe, I feel like maybe 8 or so, 7 or 8 total times am I going to have to do this. Because why is that? Well, intuitively, number 1 a moment ago was here. But how far did she move down the list? Well, just 1 step. Now, 8 made some pretty good progress. So it seems like there's some asymmetry in the benefits of this algorithm. But again, anyone who was too small to be on that end is only stepping 1 at a time. These small numbers like 1, number 3, are bubbling up, if you will, pretty slowly to this side, whereas 8 is already in place. So if that suggests, in the worst case, that 1 started over there, let's say, well, each iteration of this loop, ++++++, would number 1 just move 1 step, which means I've got to go back here, do it again, do it again, do it again, as many as 7 times, or really n times, n being 8, you know, give or take, to do this again and again. So let's do this once more. And this time I won't deliberately go through all the verbiage. Let's see if you guys can execute now down the line. So ready? It's iteration number 2. OK, now what do? So I reset. So it feels like if you're thinking this through, I'm doing +++++++++, then I'm going all the way back around. Feels like we just have a nested loop. You did this in Scratch. You might have done this in C already, maybe with Visionaire if you've already started that part. So, and even Visionaire can be done without a nested loop. But it feels like a nested loop because I'm looping again and again and again. And then I've got this bigger outer loop that's bringing me back home after 8 or so steps. All right, let's go 3rd round. OK. OK, OK. And now, what do? OK, so I go back to the beginning. All right, so hopefully we're almost there. Now can I stop? All right, so maybe intuitively you might think, yeah, it's right. But again, you don't have that aggregate view. The only way we're going to know if we're done is to keep checking pairwise, 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 pairwise. Now am I done? So visually, yes, but on this iteration, I made a swap. And unless I've added some very sophisticated conditions or checks, all I know is I just made one swap. So surely if I made one swap, I might not be done, because maybe that number that I swapped has to bubble down even further. So really, the only way to do this for sure is to now do one additional pass and say, And now maybe I have a counter called counter. And every time I do a swap, I increment this by 1. Right? And now my counter is still just 0. So now I'd be stupid, frankly, to go back to the beginning and do this again, do this again, do this again. So that then begs the question, in total, how many steps does this algorithm involve? How much work does this algorithm involve? Well, in the best case, let's start with the easier one. In the best case, this group of folks did not line up like that. They lined up right like this. In which case, how many steps does it take for me, the computer, to sort n individuals? OK, we have disagreement. Everyone here says 1, and this guy says 8. So which is it? Well, it kind of boils down, frankly, to semantics. What do we mean by step? Do we mean one outer loop? Maybe. Do we mean one individual step? Maybe. I'm going to say minimally, let's say 8, because let's literally count any line of code that I execute, or physically any step that I take. So to know that all of these folks are sorted, minimally, I'm going to have to check each pair, keeping track of how many swaps I do, still 0. Now I can quit. Even though I was in a loop, some of you might have used a special instruction in C called break that will break you out of a loop. You might not have had occasion to use this before, but just because you say a loop needs to iterate 8 times or n times, you can break out if you want, if the just situation warrants at any point. You could do this with Scratch, too, with the stop sprite block or stop script block as well. So now, what about the worst case? Well, what was the worst case? If you guys don't mind for the visual, can you arrange yourselves in the worst possible case? Worst case is not random, right? Actually, worst case for our purposes is the most amount of work that I might have to do to fix this problem. Now, in fact, this is the worst possible case, because now everyone is in the wrong position. And in fact, number 8 is way the heck over here. Number 1 is way over there. This is the worst possible case. That was actually somewhere in between best and worst. How many steps now is it going to take me to sort these folks? So 64, if you count it up. And can we generalize if these are actually n individuals as opposed to 8 specifically? Yes, so n squared. And where does this number come from? Why n squared? N times n. Oh, what's that? Yeah. So it's this inner and outer loop. The inner loop is obvious to see, because I keep taking all these steps across the stage. Every time I check for swapping opportunities, I'm taking 8 or maybe 7 steps. But for simplicity, let's just round up to 8, so we don't have to do n minus 1 all the time. But let's say this took 8 steps to get here. But now, in the worst possible case, I'm going to have to reset myself like a typewriter all the way back to the beginning. One more time, then another time, then another time. And if number 1 needs to move, let's say 1, 2, 3, 4, 5, 6, 7. If number 1 needs to participate in 7 swaps, which is really almost 8, so let's call it n, or we could really be pedantic and do n minus 1. That's n swaps. So on each iteration, she only moves maximally 1 step. She only bubbles up a little to this end. So to get her all the way here, I need to take n steps this way. And I need to do that as many as n times around. So in the worst case, to sort n individuals with this algorithm, it would seem to take, give or take, n squared, n times 2 number of steps. Now, 8 times 8, 64. That's not that bad, right? It felt like the intuitive human way was a little faster. But n squared isn't that bad. But what about when n is not 8 but 10? So that's 10 squared, that's 100. Or 100, 10,000. Now we start getting very quickly to much larger, scarier values. And this feels like it could very quickly start consuming a lot of resources. So can we do better? Let's try one other approach. If you guys could reset to this random approach, so we don't always consider best case, worst case. Let's see if we can't do something a little different. So that was the simplest, most naive algorithm I could come up with as sort of a newbie computer, swapping the things that I see next to each other. Let's try to leverage the common sense that most of us have, that all of us have in this room when it comes to finding the smallest number. And let's just grab the smallest number, then look for the next smallest, then look for the next smallest, right? Because odds are when you glance at these numbers and you're told sort them, you probably latch on to the number 1 first. Maybe the number 8 if you prefer to work backwards, but at least the number 1, then 2. So let's see if we can't leverage that. So again, visually, if you could flip your papers around, this is what the computer sees in advance. I just know there's 8 elements. I can't see them all at once. So now if you could go back to normal, now I'm going to be the computer, and I'm going to look for the smallest possible value. All right, so 4. he is the smallest possible value at this point in time. So I'm going to make a mental note, or in computer terms, I'm going to use a variable to remember 4 is the smallest, and he's at location 0. All right, now, ooh, disqualified. He is no longer the smallest value. I've now found number 2 at location bracket 1. Now I'm going to remember that, and I'm going to forget about him. Right? Because it's a lot easier to keep track of one number than 2 at once. So now I keep looking, because maybe you're not number 1. So you don't change my variables. Definitely not. Ooh, 1. We've already ousted number 2. So here's the smallest possible value at location 0, 1, 2, 3. At location 4, so I should remember that. Do I now know I found the smallest? Right, so not technically no, visually obviously, but technically no, unless I was given an assumption. Here are 8 numbers, the smallest number is 1, but I was just given 8 numbers in random order. The only way I know number 1 is in fact the smallest is by continuing a total of 8 or n steps. But now what do? I remembered with some variable that she's at location 4. So what can I do? Well, unfortunately, this is an array. An array thus far, we've fixed the size. When you create an array, as we've seen, like an array for quizzes, we said 2 quizzes go here. And we used a constant at the time. And in fact, in C, unlike some languages like PHP and JavaScript, we'll see, when you declare an array, it's a fixed size. Now, this is a problem, because I might want to move number 1 to the start of this list, but there's no room, right? I only have 8 slots. I have 8 numbers. I can have temporary variables, so I could pull you out, if you will, from the array, leaving kind of a duplicate or a gap in it. So what are my options? How do I move number 1 to her appropriate place? So I could swap, right? What could I do? You know, he doesn't need to be there, right? I definitely don't need number 4 there, or really in general, anyone other than 1 there. So why don't I do that? And actually, before I do that, what's an alternative before we do this right? Right, I could just, guys, could you, that way, yeah. But wait, that looks obvious, looks intuitive, but that's now what, 1, 2, that was 3 steps, because each of these variables, or each of these ints, has to be moved deliberately by the computer with a line of code. So that's 3 steps to move these guys over, maybe 4 to move him over as well. Let's take the simpler approach. 4, again, doesn't need to be there. These numbers were given to me in random order. Who cares if I mix them up even more, if I don't care where they are just yet? So let's move number 1 over here, number 4 over there. And now this is 1 swap, not 3 or 4 total swaps. Now what do? Well, I'm at the end of the list. Now, nicely enough, I can have a little optimization. I never again need to look at number 1, because I already have decided, very good, because I've already determined she's the smallest. So it would just be a waste of CPU cycles to start here again. So I can maybe have another variable that says start this time at number 1, not at location 0, start at location 1. So here we go. Number 2, I found him. He's already right here. But I don't know that necessarily. So now you might be thinking, well, why didn't you just remember this the last time? And I could, but that's a different algorithm. That's more memory. Right now, I'm just using a couple of variables to keep track of who and who's where and what they are. So 2 is currently the smallest, so I'm going to remember that. 6 doesn't beat him. 8, 4, 3, 7, 5. So that's another n-1 steps, because I didn't bother looking at number 1 again. So that's almost n steps. He is, in fact, in the right place. I don't have to do any work at all. Now let's continue. I can move my left boundary here. 6 is currently my smallest number. Not beaten by 8. Oh, beaten by 4. 4 is now the smallest. Oh, 3 is now the smallest number. Nope, nope. I've made mental note of where 3 is. What do? Swap 3 with 6. And now I'll stop telling the story verbally. If you guys, I'll just point, can execute now. So actually, this really isn't very clear if I just point and say nothing. OK, so 4 is currently the smallest value that I found. So where do we move you? So we swap these. And again, it might seem that 8 is moving into his position. And that is true, because presumably 8 is bigger and is moving up. But for the most part, these swaps are just moving random numbers to other random locations. So we're not actually making the problem any worse fundamentally. So now 8's my smallest. Oh, no, now 6 is. Now 5 is. So 5. All right, good. And now 6 is my smallest. 7 is my 6 is my smallest. 6 is still smallest. 6 is still smallest. And so no swaps. Now I do the same thing, the same thing. So this begs the question. This was a little more real world, a little more human oriented, because I just implemented my common sense. I found the smallest number, put her in place. Found the next smallest number, put him in place. And then repeat, repeat, repeat. So how much time, how many steps did this algorithm take? So it's not n factorial. It kind of feels like one of those expressions, but that would actually be really bad, right? That's 8 times 7 times 6 times 5 times 4. That gets really big quickly. So it's actually not that bad. And log n, it's not that good. n squared. So you know what? It turns out it almost is. It's not as bad as this. It's almost n squared. It feels like we had some optimizations. We stopped looking at 1, then we stopped looking at 2, and we only took as many steps as we had to do. And on each time, I didn't just blindly swap. I actually looked for the optimal position for someone by plucking out the smallest. And yet, I claim now that this is still roughly n squared. Why? Well, let's take a 5-minute break. Give these guys a round of applause, and we'll be back in 5. Thank you. You guys can keep those. If you could just meet the TFs over there, that'd be great. OK, so the cliffhanger that we left off with was how much time does selection sort take vis-a-vis bubble sort. So bubble sort, we said, pretty much takes n squared comparisons. So n squared, steps rather, is something like bubble sort. In the worst case, oh, actually, I'm the only one who knows it's called bubble sort. So the first algorithm we looked at, and I was kind of trying to hint at this by using by saying bubbling this way, bubbling that way. In as much as when we compare values, one of them might bubble up that way, and the other one might bubble down this way. The world generally calls that first algorithm, where we just did pairwise swaps, something called bubble sort. And what's nice about it is you can actually code it up in any language very, very straightforwardly. But the downside is it doesn't feel like the most efficient thing. How slow is it? Well, we'll see and feel that in just a moment. But in the worst case, it was, in fact, n squared. But in the best case, it was just n, right? In the best case, when I was handed all of the humans in the correct order, I just had to do a sanity check once down the list of n people to see, I didn't make any swaps. Therefore, I'd be foolish to do that again and again and again. So I can terminate that algorithm early after just n steps. Now, this second algorithm we did might be called selection sort. That's what the world generally calls it, in as much as you are selecting on each iteration the smallest value. Now, you could completely flip it around and just select on each iteration the largest value, but the algorithm would be the same in the end. So selection sort, it wasn't as clear at first what the running time is, what the performance of this actual algorithm is. But let's see. So with selection sort, to find the smallest element, it might take me what? N steps. I have to look at n values because number 1 might be all the way over here. Then I swap, but then I leave number 1 in her correct place. And so now I move on to look for the next smallest element, which might be in the worst case where? Might be over here. But this is only 7 steps this time. So it feels like an optimization is brewing here, right? Because 1, I don't have to keep looking at, as I said. I'm just now looking for the next smallest value, which happens to be 2. I find him maybe worst case over here. I swap him. That takes just a single step, or maybe 3. And here's where I'll start to wave my hands at some implementation details. But visually, swapping those 2 people, we can think of that as just 1 step. It's 1 swap, 1 operation. So now I did 8 steps to find number 1. Took me 7 steps, worst case, to find number 2. Might take me 6 steps, then 5, then 4. So it seems that we have this kind of process, 8 plus 7 plus, and then down to 1 to find the very last person. Those of you who like looking at formulas like this might see a little something like I equals 1 up to 8. All right, so a little summation like that. And what does this actually work out to be if you use that cheat sheet in the back of a high school math book? All right, so if we actually do this out, 8 plus 7 plus 6 plus 5, I believe this works out to be n times n minus 1 over 2. Is that right? Right, so how did I get to that? Well, frankly, you can, what's that? N plus 1? OK, n times n plus 1 over 2, I get the end result of a formula that's what? If I actually multiply this out, well, this is n squared plus n over 2. So, you know, there's an n squared in there. Is it n plus 1 or n minus 1? OK, plus 1. So n squared plus n over 2. Now, that feels better than n squared alone was, right? Because even though this is n squared plus n, then I'm having it. So this actually feels pretty good. But here's the thing. When it comes to actually implementing algorithms and analyzing algorithms, it's in the context of computers, these kinds of constant factors, like the number 2, this really isn't all that interesting. I might claim selection sort is twice as fast, give or take, than bubble sort, because look, it takes half as many steps. Now again, n squared plus n, I'm kind of waving my hands at some of the terms here. But this 2 kind of means that you have the running time, the amount of time it takes for this algorithm to run. But you know what? Who cares, right? Every year, CPUs and consumer PCs seems to get faster and faster, so that this year I might have a gigahertz computer. Next year, I'm going to have a 2 gigahertz computer, which means next year, selection sort will be twice as good as it is today. Right? So it's hard to make claims with algorithms that are just these constant factors better than one another, because again, with the right hardware, you can kind of hide those details. What we really want to do is find an algorithm that even if computer speeds double next year, well, my algorithm itself gets even more than twice as fast. We really want to ride the curve as best as possible. But for now, we're going to wave our hands for a bit until we get more precise. And this is to say, if selection sort takes n squared plus n over 2 steps, this isn't that interesting. And you know what? Even this term here, maybe this is relevant when it's n squared. So that's 64 plus 8. That's 8 additional units of measure more than 64. That's non-trivial here. But what if now n is a billion? A billion squared plus another billion, that's actually not all that much more as a relative proportion. So you know what? Forget this. This, in the long term, as n gets bigger, this is kind of a meaningless addition to the formula. So we're going to claim for now that selection sort 2, in the worst case, is actually pretty much comparable to bubble sort. Not if you line up the numbers precisely, but at least big picture. If you think in terms of large n and you compared the graphs, as we'll do in a moment, that these formulas make, it's pretty much n squared. And in fact, there's a problem with selection sort. What if in the best case, I'm handed 1, then 2, then 3, then 4, and I try to sort those elements with bubble sort? How many steps is it going to take to sort n people in the best case with selection sort? It's the same, right? Because even though it felt like this nicely intuitive algorithm just keeps selecting the smallest possible value, well, what's going to happen in the best case? They're all lined up from 1 to 8. I find number 1 here, and I say, OK, he's the current smallest. Then I find 2, 3, and not until I get to the end do I realize, well, that was stupid. I found him in the very first step. Now let me go back to the beginning. I don't have to look at him anymore, because now I have to look for the next smallest. And so I'm looking now for 2, right? So now where's the next smallest? Well, 2's right here, but maybe there's 1.5 or something like that over there. I have to keep looking and looking and looking. So here's the downside of selection sort. In the best case, it too is n squared. So while it might feel more intuitive, might feel like the more obvious algorithm, we've just made the situation worse, because I don't know in advance what these elements are. So let's add some nomenclature here that computer scientists are fond of using. There's a symbol that the world generally uses to describe what's called the worst case. And this is a capital O, often written in italics. So this is what the world generally calls big O notation. And if you say an algorithm is in big O of n squared, that just means in the worst possible case, if you hand it everything completely out of order, it might take as many as this many steps. Now, in the best case, we use a different symbol, a Greek one this time, omega. Omega just is the fancy way of saying, in the best possible case, this algorithm might take n steps. So these two correspond to bubble sort's worst and best cases. Now we can use the same symbology for selection sort. And so we now have big O of n squared for the worst case, omega of n squared for the best case. And just to toss out one additional piece of jargon, if you say theta of n squared, that just means it's essentially in both big O of n squared and in omega. So in other words, if these are the same, you can then whip out this notation as well, this theta notation. Now, why do we use this? Because it's just a nice shorthand way of saying best case, worst case. And we can now start to talk about the efficiency of our algorithms. We can talk about the quality of their design in terms of their performance in a way that's not CPU specific. Doesn't matter if it's Intel Inside or anything else, because now we're looking at a higher level than we have in weeks past at the underlying operation, swapping two things conceptually, or stepping down an array conceptually, step after step after step. So let's see if we can't visualize a couple of these algorithms in a more rapid way than humans here allowed for. So this is a little program that's available online. We've linked to it on CS50's website. I switched over to one of the TF's PCs here because it doesn't work properly on a Mac, unfortunately. The buttons don't appear on the bottom, but that's fine. Just realize if you play with it on your Macs, you'll be missing some of the demo. And notice that in the bottom left-hand corner of this little applet, happens to be written in Java, I can choose a whole bunch of sorts. And I've pre-selected bubble sort. That's the first thing we started with. You can specify what the array is going to look like at first. You can specify a time delay here. I'm going to go ahead and just click Start, and we'll see what happens. So what you see on the board now is just a visualization of what we did a moment ago with humans. Each of these bars represents a number. The taller the bar, the bigger the number. The smaller the bar, the smaller the number. So small bar might be 1, big bar might be like 100. And what's happening here in red is that this algorithm, much like my feet on stage, is looping from left to right, and on each iteration it's comparing two elements, making them red, and then swapping them if in fact they are out of order. And even though this is moving at a pretty good clip, you can see a couple of features here. One, it's kind of boring, right? It's kind of slow, even though those bars are moving at a decent clip left to right. But clearly, visually, are the larger elements bubbling up to the right-hand side, and gradually are the smaller elements bubbling down, if you will, to the left-hand side. So it's almost done, almost done, almost done, almost done, almost done. And it only makes them red when it actually swaps them. OK, done. And down here, if you're curious afterwards to play with the demo in more detail, it actually counts how many comparisons you're making, how many swaps you're making, and so forth. So now let's do this. Let me go ahead and click stop here. I'm going to change the algorithm to selection sort. I'm going to use the same speed, to be fair, and click start. And now less seems to be happening per unit of time. There's less flashiness. But notice now highlighted in red is the smallest element encountered. And as soon as it's found, by confirming, by going all the way to the right, it drops it into place. So visually, this algorithm is working kind of the opposite direction. The end result is, of course, going to be the same. And it actually felt a little faster. And it absolutely did fewer swaps, because this time when we're swapping, we're really swapping it as far away as we want. We're not just doing these adjacent swaps. But this, too, if you actually count out the number of steps in the worst possible case, you'll see these numbers n squared. You've got 100 elements. It's going to be 100 squared possible steps, or comparisons, or swaps. And same deal for bubble sort as well. So that then begs the question, can we do different? And why would we want to do different? Well, let me toggle back here to these visuals and see what the implications are for algorithms that are, in fact, n squared, or just in general, not so well implemented. So this is a little chart that I just happened to make up with Excel. There's not all that much going kind of not the best fidelity on the screen here, but I'll point out the details that are actually important. Here, thanks, got it. OK, so on the x-axis here, we just have n. So this happens to be 0. This happens to be 33, 66, and so forth. Doesn't matter what they are. Just on the right, on the x-axis, there's a value of n, and it's increasing. So this implies more and more humans, or more and more numbers to sort. Meanwhile, on the y-axis here, this is meant to depict time. So if you have 33 elements, as this suggests, according to this chart here, it's saying this takes 5 units of time. And this means more units of time. And if it's up here, that's even more units of time. So the numbers, frankly, are irrelevant. It's really the curves of these things that are worth considering for just a moment. So there's 3 different graphs here that I made with Excel. One represents n. So the little diamonds are the ones here on the left-hand side. And even though it's not going up at a 45-degree angle based on how I did the axes, it's obviously a straight line. An algorithm that takes n steps means if you increase the number of humans, or the number of numbers, by 1, it's going to take you 1 more step to count it. So consider, for instance, bubble sort in the best case. If I didn't have 8 volunteers, but I had 9 volunteers, well, in the best case, it's going to take me 1 additional step to check that 1 additional human, because I just have to take 1/9 step over here. So that we can see as pictorially as this relationship here. Now suppose I come up with a smarter algorithm, as I did in the first day of class. Recall that the simplest algorithm for counting all you guys is 1, 2, 3, 4, 5, 6, 7, 8. This takes a while. But it's slightly faster. Actually, it's twice as fast if I use that little grade school trick of 2, 4, 6, 8, 10, 12. And so now that algorithm is, in fact, twice as fast. It's still a straight line. And that's what this one with the squares represents. So according to the axes I've chosen here, it's still a straight line. But notice that it moves at a lesser gradient. So that's good, because it means as n increases, the amount of time taken to count, the amount of time involved in counting people in 2s instead of 1 obviously is less than if you're just counting them 1 at a time. But here is really the end game, this thing here. So recall that the other algorithm we deployed in the very first day of class was that self-counting algorithm, where you guys all stood up, and then half of you sat down, half of you sat down, half of you sat down, so that we went from like 500 to 250 to 125. 5, and so forth, until there was just one, in theory, person standing. Now, it took a while because there was a lot of social issues and coordination of all that going on. But in theory, on each iteration, that problem was getting halved, 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 just like the phone book, getting halved, halved, halved. Well, what does it look like when you have a problem again and again and again? Well, it looks like this chart here. When we describe that algorithm as logarithmic, or log base 2 of n, this is what it looks like. And again, it's the curves here that are interesting, because it looks like if I'm counting people in Sanders the naive way, one at a time, I mean, this is going to take a ridiculous amount of time. The chart literally goes up to the roof. Now, it's slightly better if I count you in 2s, but even that, eventually for large n, it's going to take a ridiculous amount of time. But if we use something like the divide and conquer strategy of the phone book, or as applied to humans, having half of you sit down, half of you sit down, this is when this curve gets amazingly powerful, right? Literally, on that first day of class, we could have had like Justice come back into Sanders, right? Doubling, more than doubling the number of students in the room, and yet the algorithm you guys were applying, one more step, right? Because we could have made all of Justice sit down the moment they enter the room, and we just, right? We know that we've taken a bite out of the problem that's half as large as n itself. So this is really the sort of golden ring that you're after when you're trying to come up with the most efficient or the most luring algorithm possible. And the payoffs, as this chart suggests, are huge. This is 130 here. This means if we have 260 students, that's over here. And then 500 or so over here. That chart, or that graph rather, is flatlining in this way, far more so than these things. Now, of course, we cannot sort n elements in log n time. Right? Log n seems to be, again, what we're after, the holy grail of algorithms, because look how much better it is than anything we've looked at thus far. But I claim we can't sort n individuals in logarithmic time. So neither of these algorithms were that good. And I don't think I can come up with one that's good. And intuitively, why might that be the case? Why can you not sort n people or n numbers in log base n of time? So clearly, yeah. Yeah, there's this one gotcha. You can't possibly sort n individuals in less than, say, n time, because you don't know if they're actually sorted unless you actually check that list, right? Otherwise, it's guesswork. Now, we the humans might glance at the list, sorted. But how did you do that? Well, maybe unbeknownst to you or your brain, you actually did skim that list, at least one eye movement for each person up here. So that's at least 8 steps. So this might work for searching, and that's what this might work for counting, searching the phone book, counting the students. But for sorting, we need to spend a bit more. Well, what do these algorithms feel like? Well, here's a different chart, different axes, but again, it's the shape that we care about. So here is the same chart, but we've given us more of a y-axis. Here is what I will call n. So this is, if you increase the number of students, your algorithm increases by 1. It's a 1 to n ratio here, or rather, it's a 1 to 1 ratio. Here is log base 2 of n. So when you, right, this is how you can kind of mislead people with statistics and charts and consulting and all of this, right? Change your axes, and look how n looks, not all that much worse than log base 2 of n, right? Your clients might as well buy the n algorithm. It's not all that much slower. But notice here, if we actually are now looking at algorithms, as we're going to start to in class, that take maybe n log n squared. Or actually, this is if we look at algorithms that take n squared time, like bubble sort and like selection sort, I mean, my God, if only we could sort n individuals in just n time. You really start to feel the difference. Again, even irrespective of the axes, the shapes of these graphs suggest that if you can avoid n squared, you really should. In fact, if we zoom out even further, there are some algorithms in this world that are believed to be exponential. This isn't even as bad as factorial. Exponential here at top, if you have an algorithm that takes 2 to the n steps, which we may discuss briefly in time, for more on this, CS121, CS124, I mean, my God, this is absolutely an algorithm to be avoided, because here you are at like 200,000 or so steps, and wow, here is n down here, at which point all of these algorithms look better and better. But this is the takeaway. When you start looking at problems like Facebook faces and Google faces, and n is actually big, these are the kinds of curves that are particularly alluring for someone. So can we do better? And how can we describe these things? Well, again, we got big O, we've got omega and theta. Let's see if we can't describe yet another running time here. But we need a tool for this. So we have talked certainly about the phone book, sort of ad nauseum at this point. And that was an example of divide and conquer. Divide the phone book in half, and then do it again, do it again, do it again. And therein lies kind of the insight of divide and conquer. We did this too yesterday, on Monday, with the second array. We dived into the middle of the array, then we dived into the middle here, then the middle here, and voila, there was our element, the number 50. So when you do something again and again and again, and the only thing that's changing is really the size of the problem, the steps you are executing are still the same. I'm still tearing a phone book in half. It's just half as big now. I'm doing it again. It's now a quarter of as big, but it's still the same algorithm. Well, this is in general known as recursion. And we can write functions. And I did this just kind of for fun the other day. We can deliberately write functions that recurse by calling themselves. Now, what do we mean by this? Well, in the context of C, we can write a function, and surely that function can call itself. If I define a function called foo, if I want foo to call itself, I just have to write the word foo, open parenthesis, close parenthesis, semicolon, inside foo itself. But bad things happened when I did this last time. What happened when I wrote literally a function foo that called itself? So I got a seg fault. Now, why was that? Well, again, just think back to the building blocks we've been looking at, right? We have memory in our computer. We keep drawing it as a rectangle. Every time you call a function, you add a frame to that stack. In other words, you ask for some memory, and conceptually, it's like putting it on top of the stack of memory you've already asked for. So you call foo, you call foo, you call foo, 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 foo. What eventually happens? Right, you run out, or you hit some other memory that doesn't belong to you, and that's something we'll see before long called the heap. But in short, doing this again and again and again is bad. So recursion does have this risk in it. If you do the same thing again and again, but each time allocate memory, you might run into some trouble, but perhaps it's nonetheless a technique we can leverage. So let's take a look at one piece of code here that was among the printouts from Monday. And this is something called sigma 1. Just out of habit, I'm going to start using VI sometimes instead of nano. It's just another text editor with more arcane commands, but it does the same thing. I'm going to scroll down and introduce this relatively tiny program. So this program here has a main function. And the first thing this function does is asks the user for an int. So this is actually a good use of the do-while construct, because recall that do-while tells the user to do something and maybe gets something from the user. But if the user is being difficult, I can force it to loop again and again after I've checked that value. So this chunk of code here, as the comments explain, I'm forcing the user to give me a positive integer. Not a negative, not 0, but a positive integer. Now, at this line in the story, I'm apparently declaring a variable called answer. It's of type int. And I'm assigning it the value of sigma. So I chose sigma based on this symbol here, just to be clever. But sigma is apparently a function that I wrote. It takes one argument. I'm passing it apparently an integer. So let's see what it does. Well, actually, this is pretty simple. It looks a little cryptic at first, but this is like day one stuff now, right? Sigma is going to return an int. It's going to take an int as its argument, and I'm calling it m just because. I'm a little sanity check. I don't want to get into an infinite loop here by accident, so I'm making sure m is not less than 1. If it is, I'm returning 0, just so bad things don't happen. And now what am I doing? I'm declaring a variable called sum, initializing it to 0. And then this loop here, well, actually, it's pretty straightforward. I starts at 1, goes up to and through m. And on each iteration, plus equals just does what? It adds the thing on the right to the left. This is equivalent, and it's just shorthand notation for saying sum equals sum plus I. It's just a little more succinct than that. So in the end, the sigma function just returns the sum of all of the numbers from n down to 1, or down to 0, which are equivalent. All right, so this is one way to do it. Let me go ahead and go back to the original here. So this is plus equal 1. Let me go ahead and compile sigma 1. I'm going to run sigma 1. And I'll give it a positive integer of 8 people. All right, so 36. So that's 8 plus 7 plus 6 plus 5. Let's do it for 10. All right, 55. OK, let's do it for 100. All right, so this program seems to work. And frankly, it's doing this a lot faster than I could off the top of my head. So we have a nice, useful program here. But can we implement it in a different way? Well, this isn't necessarily the best way to implement it, but it's a nice way of demonstrating this idea of recursion in a very simple context. So this is version 2, sigma 2. And here we have same code. Get the int, put it in n, and make sure it's not less than 1, and then call sigma again. And I'm going to print out the answer. So apparently, main is identical. So let me scroll down to sigma. And here is something that's beautiful to my eyes, at least. So what does this mean, sad though that is? So it returns an int. It takes an int. But now I just have four real lines of code. And even those are not all that interesting because one's an else, if and an else. What am I doing? Well, first, this is pretty much the same sanity check as before. If m is less than or equal to 0, just return 0 right away so that the user doesn't hand me a negative number and completely break this program. But notice this. All that work I did last time using a for loop and incrementing I and the sum and all this messy syntax, it looks like I could just do this. This is an example of recursion, right? Just as I could look for someone in the phone book by looking in the middle, then checking left or right, then doing it again. Well, technically, you could sum numbers in the same way. If you hand me the number 8, I can say the answer to sigma of 8 is 8 plus sigma of 7. And I can completely punt on the rest of the problem and let you deal with that, right? You ask me for sigma 8. I say it's literally 8 plus sigma 7. Well, now you come back to me and you say, fine, what's sigma of 7? And I sort of smart ass say 7 plus sigma of 6, right? And again and again. Now, I'm sort of picking a contrived example here. But what's nice is, just like with the phone book, just like with the counting students, we can take a byte out of this problem. Maybe it's only size 1. It's one number. But I can take a byte out of this problem and then apply the exact same algorithm to the slightly smaller problem. And if I code this correctly, notice what happens. If I code this correctly, I can take this small byte out. And then I can defer to who? To myself, right? If I am now the sigma function who knows how to compute this, even though it's in this smart aleck way, well, I can just say it's m plus sigma of m minus 1. Now, conceptually, what does that mean? It means this is going to get added to the return value of sigma of n minus 1. Well, how do you compute that? Well, here's sigma. You pass it now in the number 7 instead of 8. 7 is not less than 0, so you don't return 0. What do you return? You return 7 plus sigma of 6. Now, at this point, it gets to be a bit of a mind game, right? Because now you have to keep saying call sigma, call sigma, call sigma, and you're never actually finishing any of these answers until what? When you call sigma of 0, finally, this seeming endless loop stops, because at that final 8th call, you say, well, what's sigma of 0? And I don't give you, again, this smart aleck answer. I instead say 0. And that means you can then kind of reverse the process. So you can say, OK, if the answer to the last question was 0, then it's 0 plus 1, and that means 1. Then the answer to the previous question was 2 plus that. And you can kind of unwind in your mind. And it's a little hard to think of at first. But what's the end result? You can implement in, dare say, this beautiful way, this very elegant sort of logical way, the notion of summation that we just did, but using just one line of code and leveraging the code, sigma, that you already wrote. Now, what's the power of this? Well, once you have the ability to do things recursively, you're not necessarily able to solve problems in different, you're not necessarily to solve problems that you couldn't otherwise using iteration and loops, but you can solve them a lot more intuitively. And you can use a programming technique, recursion, in a way that really lends itself to the problem. And for that, let me introduce this. I'm going to pull up a different demo here. This one also happens to be implemented in Java, but it's just a visualization. As an aside, the world has come up with all sorts of sorts. We won't look in this course at bozo sort, or cocktail sort, shaker sort, but there's a whole bunch of them out there. Let's pick the ones we did look at. Bubble sort there. I'm going to pick selection sort here. And it turns out one of our favorites, because of its power, is something called merge sort. So I've zoomed in on this graph. What you see here is same kind of visualization as last time, but instead of the numbers being vertical, this guy just implemented it sideways. So in a moment, I'm going to click each of these graphs. They're randomly oriented. Small bars mean small number. Big bars means big number. And what you're going to see, assuming I click them all fast enough, is each of these 3 algorithms running simultaneously. And my claim is, as we've seen, bubble sort in the worst case is n squared. Selection sort in the worst case is n squared. But this thing, merge sort, is an example of an algorithm that's in n times log of n. So it's not as good as log n, which was the case for divide and conquer and for searching. But n log n is definitely smaller than n times n, because log n is smaller than n. So here we go. I give you in conclusion, bubble sort v selection sort v merge sort. So that is what it means to solve problems effectively. See you on Monday.